This lesson is for section 5.6, compound interest. This entire section is all about money, okay? I don't know anybody who doesn't like money, so I think this is an important section. It's real life. You're gonna like it. Well, you better like it if you wanna make money. All right, so two fundamental ideas to really understanding the whole idea of compound interest and doing all these financial calculations that we're going to be doing is understanding, one, that when you increase a quantity by 8%, you're going to multiply that quantity by 1.08. So I know this seems kind of obvious, but I do want to just reiterate. If you were to increase 100 by 8%, you would take the amount 100, and then you would add to that, your original amount multiplied by 0.08. Now, if I were to factor that out, that 100 out of here, I'm left with 1 plus 0.08, and that results in 1.08. So really, I can just kind of cut to the chase here and understand this concept. That's what I want you to understand and be able to do in your head. Now, the second very important big idea here is that when you increase a number by 8%, and then you were to increase that new total by 8%, that number would yield a larger number than if you were just to increase it by a one-time increase of 16%. So what I mean by that is, let's say we take $100 and we increase that by 8%. We're going to multiply that, like we just talked about in rule number 1, by 1.08. Now, if you were to increase that amount by another 8%, then you would take that amount and multiply it by another 1.08. So you get $116.64. Now, if you were to increase that same $100 by just 16%, you would only get 116. So it actually helps you to increase something twice by a smaller amount than it would be to take a one-time increase of that amount. You guys probably have a very good understanding of what a savings account is, but you might not know the terminology behind it, so I want to just briefly cover that with you. So let's say you place $1,000 into your savings account that has a 3% interest rate that's compounded annually. So this is probably new terminology here for you, compounding something annually. Most banks do not compound things annually, they do it more often than that, but let's just say that a bank were to compound your interest annually. What that means that is after 1 year, so it's only once a year here, they would take your amount that you have in there, that $1,000, and they're going to add 3% back to you. So they would add $30 to your account so that you now have a total of $1,030. Now, this interest is called compound interest, but it's also known as simple interest. And I'm going to actually use this terminology here, simple interest, to denote something that's only compounded annually. Okay, so it's simple interest means it's compounded one time a year, compounded annually here. The original amount that you used or that you invested is called the principal, and we denote that with a capital P. To continue with this $1,000 investment here, the 3% that's compounded yearly or annually here, I want to know how much do I have in this account after 2 years. So what we could do is, using our rule from number 1, that big idea number 1 here, we could multiply that $1,000 by 1.03 to get the $1,030, and then we can take that amount here and multiply that by 1.03 again. Now we get $1,060.90 because, again, your interest is slightly more when you do it twice because you're now taking interest on a newer, larger amount. So this calculation would be really tedious to do after, let's say, 50 years, because I wouldn't want you to have to do this 50 times. Now, I did show off to the side here that I could have made this calculation a little bit easier on myself by taking that, multiplying 1,000 by 1.03 squared. Very similar to what we talked about in Rule 2. Now, again, this calculation here would be kind of ridiculous to have to do 50 times. So let's talk about some ways to make this a little bit easier on yourself. So you have all of these formulas in front of you. Right now I'm going to talk about the simple interest one, the one that's compounded only annually. So we call it simple because it's only one time, an annual interest here. And we're going to use P as our principal, R is our rate, and T is a time period, and this is always in years. So after 2 years, we can simply plug in our important values here, our principal at 1,000, 0.03 is our rate, and after 2 years, and we come up with this calculation here and get $1,060.90. So if I said after 50 years, you would simply plug in T equal to 50 here. So that's basically our simple interest compounded annually. All right, now let's say that $1,000 investment still at the same 3% rate, is compounded quarterly, meaning now it's compounded 4 times a year. And after 2 years, what you're going to now use is a different interest rate or interest formula, and that's the compound interest formula found here, where you have n times per year. So this is multiple times per year that you're going to now be compounding that interest. Now, we talked about how splitting up that 16% interest and making that compounding twice at 0.08 was actually more, you ended up with a greater yield than you did at just a one-time interest rate of 16%. So when we look at this problem now, what we're going to do is account for the fact that they're not going to give you 3% every quarter. This is a yearly rate. The 3% is over a year, but they're going to break it up 4 times. So we take that rate, 0.03, divide it by 4, and then when we raise this power, now we have to account for how many total times they're compounding it. They're doing it 4 times a year for 2 years to give you a total of 8. Now, just as we should expect, this total is actually higher than the total when we did an annual interest only. So, by splitting up that 3% and compounding it quarterly, we are gaining a larger yield here. It's not much, it's not even a full dollar, but it's still more, than you would have gotten before. So, the bank is going to cut this off. Actually, if you give a total here, you want to make sure you truncate that amount. So even though I do have, a 1,000th decimal place here, they're going to truncate that value. Now, they keep track of all that. They don't give you that amount of money because for them, that accumulates a whole lot of money. That's like billions of dollars. When it's, for you, it's only pennies, but when they take pennies away from lots and lots of people, that's a lot of money that they can keep track of and keep for themselves. Before I get into continuously compounding your interest and talking about this formula over here, I want to talk more about the vocabulary terms, the effective and the nominal rates. And you're going to see that this 3% is called a nominal rate, but it's not actually the interest rate that you receive after the end of that year or even after 2 years. So let's talk about that idea of nominal versus effective rates. So let's say you want to go buy a car or a house or boat or whatever you end up wanting to buy, and you have to take out a loan in order to purchase it. Well, they're going to tell you an upfront nominal rate, which is really the rate in name only, nominally. Okay, it's the rate in name only. So it's the amount that they might advertise, but really the effective rate, or also called the APR, is the rate you actually pay in 1 full year of having that loan. So now coming back to our original investment problem here. That 3% interest, that was our nominal rate. So this is without taking into account the fact that you are compounding quarterly. Now, if I wanted to know the effective rate here, what I would need to do is take a look at this portion of that formula. Because, again, this goes back to the original types of problems that we were doing where we took that $100 and we said, I'm just going to increase it by 8%. What you're going to do is multiply that by 1.08. That 0.08 here represents the rate that you're increasing it by. So here we have our original principal. We're multiplying it by this amount here. Now obviously we're doing it more times than over here. This is only a one-time increase, so this is to the first power. So we want to take that into account here as well. Now to find the effective rate, what you're going to do is say, all right, I have 1 plus my nominal rate that's been cut up 4 times, divided by 4. And it's to the 4th power because we're going to say it's only it's 4 times but multiplied by 1 because I always want to have my effective rate given after only a year. Okay, so this would give me the effective rate. Sorry, this isn't writing all that nicely in this software. But that's how I would calculate and compute the effective rate here. And after computing that with my calculator, I get 1.03033 and some other decimals after that. But you can already tell that this is larger than that original just 3% because you do have these decimal places afterwards. So it's not, 3.1% or anything even that high, but still it is larger. It's 3.03% of an effective rate. So that's the actual APR of that interest as opposed to the original nominal, which is only accounting for the original interest rate. It does not compound or account for the compounding that actually happens. So now the next thing I want to do, I just wanted to clean all that up, but I want to just stress the fact that you don't really have to memorize this formula. If you can understand the basic concept that you take that $100, and if you want to increase it by 8%, you multiply it by 1.08. It's that same idea here where you have your principal amount, and this is going to be some number, always 1 plus your rate. Now your rate will be affected whether it's, compounded quarterly, annually. If it was annually, it would be that rate divided by 1. So in this case, that interest rate was just compounded one time. So it was a yearly amount. And then you raise it to however many times you compound it. So if you compound it only one time, that's why we're raising it to a power of 1. Now, if you were compounding that interest rate quarterly, then we would take that 0.08 and divide it by 4, because we have to split it up. The bank's not going to give you 4% or 8% 4 times. They're going to give you 8% over 4 periods. So you're going to now raise that to the 4th power. So really, this doesn't have anything, you don't need to really memorize it as long as you understand the basic concept of this. And I think this is a really easy concept, and it's just stretching you a little bit to have to understand where these numbers come from and why they I think make a lot of sense. Perfect sense, and that's why math is so awesome. Okay, now in front of you, you guys are seeing a table that shows what you would earn after a year if you were to invest $1 at 100% nominal interest rate. So essentially you're doubling your money. But that nominal, right, we know what this means. That means what their advertised amount is. But we know that if we were to compound it more than once, that we're going to get a slightly higher yield than just double our money. So you do see here that if we compound this one time, so just annually here, and we use our formula that we were talking about earlier, where we take our principal amount. Now each one of these should have $1 in front, but I didn't bother to put that in, because I think you get the point that you're investing $1. That's why I specifically chose $1. But if you were going to use your rate, remember your rate, 100%, written as a decimal, ends up being 1. So that's where this 1 is coming from in all of these fractions here. So we're going to take that 1 and divide it by the number of times that we are compounding it. In this case, since it's annually, it's just divided by 1. And we raise that to the number of times that it's compounded. Okay, so we end up with double our money if we do it after 1 year, and it's only a one-time compounded interest. So we get $2. All right, now if we do it semi-annually, wow, you get a whole quarter. That's awesome, actually. That's actually a lot. If you were to do it 4 times, you get up to about $2.44. If you do it monthly, so 12 times, now we're taking that rate, that 100%, and dividing it by 12 and raising it to the 12th power here to get $2.61 approximately. Now, as we increase the number of times that we compound it, let's say we go up to daily, we end up with this number here, $2.71 and some change here. If we do it hourly and we really start raising that amount, do you guys notice something significant about where it ends up? I hope that you recognize that as E. Remember, Andrew Jackson, right? Fun. I know you guys love that story. So you do recognize this as E. So that's where that new formula, your interest is your principal, multiplied by E to the RT power, PERT, as I like to call it. So that's where that's coming from, because eventually, if you start to compound something continuously, so not just every second, but literally all the time, you're compounding it continuously, it eventually becomes E. So now that you know where this formula is coming from, okay, I'm going to just do a really basic example using the same numbers that we did before. If you invest $1,000 at 3% that's compounded continuously now, after 2 years, you're just going to plug in your rate here, the 2 years, and your $1,000 principal to get $1,061.83. And notice I did truncate this value again. I cut off all of that because the bank will do the same. And that is slightly higher, not a lot higher, but it is slightly higher than when we invested in something that compounded quarterly. So you do see that as you compound things more and more often, you make a little bit more money. Now, mortgages compound your interest rate continuously. It was like the worst thing that I ever heard in my life when I found out that my mortgage was compounded continuously. I was like, you're sucking the life out of me, and you're taking my money, not just every second, not just every millisecond, but all the time, to infinity and beyond. It's depressing, to be honest. Okay, now the last formula that I want to talk to you guys about before we actually go to solving the problems on your note sheet is this doubling time formula. So what this is saying is that the time it would take for you to reach $2,000 for our initial investment of $1,000 if it was compounded continuously at 3%, and asking how long would it take to double your money, you already know what the account's outcome, you want it to be 2,000, right? So you already know what A, this part of the equation here, equals. You know your principal amount, the 1,000, and you know it's multiplied by E raised to the rate multiplied by the time. So after a certain amount of years. Okay, we don't know what this number is. That's what we're trying to solve for. Now, when we divide out this initial amount here, we will always, always, always get 2 here. Because let's say we started with $6,000. To double it, we would want to make that 12,000 over here. When you divide that out, you're still always going to be left with 2. So we're now taking a look at E raised to the 0.03 t power. Now, if I want to solve this, I take the natural log of both sides to cancel out that E, and I'm left with the natural log of 2 equaling 0.03 t. So if I want to isolate t here, I simply divide out that 0.03. So I have the natural log of 2 divided by 0.03 equals the time period. And you're going to notice that that's exactly what we have here, the doubling time. So the time that it takes to double your investment, t sub 2, is equal to the natural log of 2, always, divided by your rate. Now this is going to give you a decimal, and that's 23.1 something. So 23.1 blah, 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 blah. So that's approximately 23.1 years it's going to take you to double your money at a 3% rate that's compounded continuously. Now, I want to show you something I think is a pretty cool trick that your textbook also talks about for you to calculate this without using a calculator. So you're going to try to approximate that value here without the use of a calculator. Alright, so I'm going to start off with what we ended up with here, the natural log of 2 divided by 0.03. So I'm going to show you a trick to be able to calculate that without actually having to use a calculator. So the natural log of 2 is approximately 0.69. Okay, so I'm taking 0.69 and I'm dividing that by 0.03. So it's approximately this amount. Now, if I actually show this as a fraction, that's 69 hundredths divided by 3 hundredths, and I know that multiplying those fractions, I can flip that and multiply by 100 thirds. Now that's going to cancel here and leave me with 69 divided by 3, which was approximately 23 years, right? We got that almost that exact same answer. We had, 23.1, but you get the idea here that you're just approximating anyhow. So that's okay that we got something that's slightly different than what, our calculator ends up giving us as an output. Now, so basically what that came from was saying, all right, I'm going to take this amount, which 0.69, I'm going to call that just regular 69, and divide that by the rate without converting that to a decimal, and take that and divide it by 3. Now, if it was something like, let's say, 69 divided by 4, we can actually change this number here. We can call that 70 if it's easier to divide that number by 4. But most often, 72 is going to be the number that you use because 72 has more things that are divisible. Or, I'm sorry, more numbers divide 72 than 70 and 69. So this is like it's called the rule of 69, 70, or 72. That sounds so weird, but we can take that, and that's how we can approximate a bunch of things. So if I wanted to find out the doubling time that it would take for an 8% loan, I would take 72 divided by 8, and I would get 9 years. So it'd be approximately 9 years. Remember, this is just an approximation. If you were to actually calculate that, the natural log of 2 divided by your 0.08 here, that interest rate, you're going to get something slightly less, which is 8.66, blah, 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 blah. There's more stuff. So this should be an approximate symbol here as well. But notice that how close we actually were to the original amount. So, like I said, this is just a way to approximate that very quickly. And I would like you to actually use this rule because I think it's way more of an effective use of your knowledge for you to be able to do this. Like if somebody would be like, hey, I'll give you a 6% rate and in no time you can double your money, you can actually calculate that right in your head. So I think that's kind of cool. Alright, so you probably hate me right now because for 19 minutes I haven't gone over any actual questions from your note sheet. But what I am hoping is that you Totally understood what I was trying to teach you, and you can do these problems all on your own. Now, if you can do that at this point, you feel comfortable enough, pause the video, go through and do these questions, and then check with the key. If you don't get these problems, though, and you still feel uncomfortable, then go through the solutions with me, which I'm going to go through very, very quickly. I'm literally going to like just speed race through these ones so that this video stays a little shorter. And then you can ask me, obviously, follow-up questions tomorrow in class. So I totes my goats, apologize. I would hate me too. But let's start with problem number 1. Okay, it says to compare the accounts for when you deposit the same amount, $12,000, into a quarterly and continuously compounded account. So you're going to have it for the same amount of time with an interest rate of 9%. We're going to compare then the nominal and effective rates. We should know what this vocabulary means, and if we don't, go back and watch that part of the video. All right, now if we take a look at a $12,000 deposit, that's our principal. We're going to say $12,000 multiplied by 1 plus, let's do our quarterly first. So our quarterly is going to split up that 9% rate 4 times, and it's going to take that to 4 times 5, a total of 20 compounding periods. And that's going to give us the amount that's in the account, okay? And I got $18,726.11. And again, I cut off that, truncated that number. Now, for the effective rate, be careful here because this is only for 1 year. So to find the effective rate, what I'm going to do is I'm going to take just this portion, because this is where the rate comes from anyhow, and I'm going to take this 1 plus 0.09 divided by 4, and I want to know that after, what my rate would be after just 4 compoundings. So not after the full 20, but just after 4 compoundings here for 1 year, and that's going to give me the effect. So this number that I get here, 1.093, blah, 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 this isn't the percentage, it's actually in here, right? Because we're doing 1 plus this amount, and that's what I really want to find out. So this is 9.3%, so it's slightly higher than that 9% nominal rate that you were getting. And that makes sense because of what we know about nominal rates versus effective rates. Now, when you do that same problem with the continuously compounded interest, now you're going to use this, PERT. So we have our 12,000 multiplied by E raised to the 5 years times the rate, 0.09. And you're just going to calculate that amount. It's going to give you a cash amount here, and then to find the effective rate, you're going to only look at this portion here, but instead of raising it to 5 years, we're only going to do 1 year. So it's going to be E to the 0.09 times 1, and that's going to be the effective rate. I'm going to go ahead and skip example 2. I think that's something that you should be able to do quite easily now on your own. Now in question 3, it asks you if you're going to need $15,000 for a down payment, how much do you need to have invested into your bank account in order to gain $15,000? Well, you're going to use, for the compounded interest that compounds monthly, you're going to use A equals P times 1 plus R over N raised to the NT power. And this is what it's going to look like. Now, when you try to solve and isolate P, you just have to get rid of this. This is just a number. You can divide that number all out here. Now, for the second part of the question, it says, what if the interest is compounded continuously? How much would you need? Well, in this case, you're going to solve again for P. And remember, E is not a variable, it's a number, so you're just dividing that out here. So you're using a different, you're using the continuous compounded interest rate, P, PERT. Okay, in problem number 4, this is really a simple interest rate because it's compounded annually, so it's only one time. So notice that I'm not dividing R at all because it's just R divided by 1 anyhow. So I've got my interest rate. This is what I need to figure out because that's what it's asking, what interest rate here. And I'm just going to solve for R. This is a really easy cubic. You're just going to divide out the 4,000 and then take the cube root of both sides, subtract 1, and you're going to be left with your rate. Pretty straightforward. Problem 5, I think, is much more difficult. It's a little bit more conceptual here. So it says, given a nominal rate of 6% per annum compounded continuously, compute the effective rate. So here we're missing a number, we're missing a time period, all of that good stuff. But let's just talk in general terms. So starting with what I know the rate, 0.06, and I know that in order to be an effective rate, the time period has to be 1. So we're going to use the continuously compounded interest rate here, PERT, and we have a principal multiplied by E raised to the 0.06 times 1. So really, all we need to do to figure out the effective rate is to calculate this portion here because the principal doesn't have an effect here on the effective rate. So I'm just going to calculate here. and it results in A equaling P times this amount here. So that means my effective rate is 6.183%. Now part B, I think, is a more difficult question because it gives you the effective rate and asks you to work backwards to figure out what the nominal rate is. So we know that our nominal rate should be smaller. Okay, so this one I think was easier. Part A was easier than what we're going to be doing in Part B. Now, taking a look at Part A, this was saying that if you had a nominal rate of 6%, that it would grow, the effective rate here, it would grow to P times this effective rate, okay? What I want to do is start backwards. I already know what my account is supposed to grow to. It's supposed to be our principal multiplied by 1.06. This is the actual amount that's left in my account after I apply that compounded continuously interest rate. So I know that P times 1.06 is equal, so the account here, I'm just using substitution here, this value is just what's in the account, is equal to my principal, P, again, multiplied by E to the R, rate period is 0.06, or I'm sorry, I don't know this number, my bad, this is what I'm trying to figure out, R raised to the T period, which again is still 1. An effective rate means that you're using it after, you want to know what the rate is in 1 year, so T is still 1. And we're just solving this. Now, I have P on both sides. This is going to cancel. I have 1.06 equaling E to the R. If I want to solve for the rate here, I'm just going to take the natural log of both sides. And I'm left with the natural log of 1.06 equaling my rate. This is my rate right here. And this is 0.05826, which ends up giving me 5.83%, which is really a good, I know that my answer is reasonable because it is less than my effective rate. All right, now that's the end of the lesson. I hope you don't hate me too much. Nice job. I hope you listen to everything and you totally get it. If not, come to class, prepare to ask some questions. I'll see you tomorrow.